Selling behind the counter. Then on the macho like Randy. The chopper go out to the granny. This nigga pull up your bandit. The killers understand it.
Hi, this is Murali Krishna from Skilltroniks Technologies Private Limited. I'm going to deliver lectures on digital image processing. Today's our topic is filtering in frequency domain. An image can be filtered in either spatial domain or in frequency domain. Spatial domain filtering involves convolution of the image with a filter kernel, whereas we can filter the images in frequency domain also by using transforms like discrete Fourier transform. So today's our topic is filtering in frequency domain. We are going to discuss the background of filtering in frequency domain and the preliminary concepts which are fundamentals of frequency domain filtering, and we're also going to discuss sampling and Fourier transform of sampled functions. Fourier transform of sampled functions. And the discrete Fourier transform of one variables. The discrete Fourier transform of one variable functions. So first of all, we will discuss the discrete Fourier transform of one variable functions, and we will extend the same concept to the two-dimensional functions like images. The main difference between the discrete time signals and images, digital images, is the discrete time signal is a one variable function will indicate in general with x of n, where n indicates the time index, discrete time index, whereas will indicate a digital image with notation f of x comma y, where x comma y are spatial coordinates. We call x comma y as spatial coordinates. We call this n as discrete time index. And whenever we talk about continuous time signals, we indicate this continuous time signals with a notation called x of t, where t is a continuous time variable. And whenever we want to talk about a two-dimensional continuous domain function, we indicate that as f of t comma z, where t and z are continuous variables. Unlike x and y in case of a digital image, where x and y are discrete in nature, and f of x comma y is a notation used to indicate a digital image, and x comma y are called spatial coordinates. And further, we'll also discuss extension to functions of two variables. Extensions to functions of two variables. As I said that the discrete Fourier transform of one variable functions can also be extended to the discrete Fourier transform of two-dimensional functions. And we'll also discuss some properties of two-dimensional discrete Fourier transform, 2D DFT, discrete Fourier transform. And we also discuss the basics of filtering in frequency domain. The basics of filtering in frequency domain. And we're also going to discuss the image smoothing using frequency domain filters. Image smoothing using frequency domain filters. Smoothing in the sense low pass filtering of images. By making the low pass filtering of an image, we will get a smoothened image. So we are going to discuss how to perform smoothing of images by using frequency domain filters. And image sharpening using frequency domain filters. We'll learn how to sharpen the images by using frequency domain filtering techniques. Sharpening in the sense high pass filtering of images. High pass filtering means we all know that we have to pass the high frequency components and we have to suppress the low frequency components in an image. Smoothing means nothing but low pass filtering and sharpening means high pass filtering. And we will also discuss various other types of filters and we'll also discuss how to perform filtering of images using frequency domain techniques. The other types of filters are commonly known as selective filters. Selective filtering. Selective filtering means either band pass filtering or band stop filtering, or it can be notch filtering. Band pass filtering, band stop filtering, notch filtering, all these are commonly known as selective filters. So we are going to discuss all these topics in this lecture series. So coming to the summary of last class, we are going to discuss the filtering in frequency domain, and first we will discuss the background of frequency domain filtering and preliminary concepts and sampling and Fourier transform of sampled functions and the discrete Fourier transform of one variable functions and extensions to the functions of two variables. That is, we are going to extend the concept of discrete Fourier transform to the two variable functions, and we are also going to discuss some important properties of two-dimensional discrete Fourier transform, and we are going to discuss the basics of filtering in frequency domain, and we are also going to discuss the smoothing of images in frequency domain and sharpening of images in frequency domain. Smoothing in the sense low pass filtering and sharpening in the sense high pass filtering. And we are also going to perform filtering of images by using selective filters. Selective filters are nothing but by band pass filters, band stop filters and notch filters. So this is the summary of previous lecture. Welcome back. Coming to the background of filtering in frequency domain. Let us start with the continuous time one-dimensional functions. We have a technique called Fourier series to find the frequency components present in a continuous time one-dimensional signal. By using this Fourier series, we can decompose or we can express any continuous time periodic signal as a linear sum of or weighted sum of sinusoidal signals. That is, using Fourier series, we can express any continuous time periodic signal as a linear sum of or weighted sum of sinusoidal signals. That is, if we consider a square waveform, it will comprise of several sinusoidal signals that we can express this square waveform as sum of sinusoidal signals. Let us say this is the sinusoidal signal with a fundamental frequency f0, and this is a sinusoidal signal with a frequency of 2 times of f0, and let us say this is one more sinusoidal signal with 3 times of fundamental frequency. Adding all these sinusoidal signals, you will get the square wave. Any arbitrary periodic function f of t can be expressed as linear sum of sinusoidal and cosinusoidal signals. We call this set of sinusoidal and cosinusoidal signals and including 1 as a complete set. Why? Because no other element exists orthogonal to the elements of this set. That is why this is called a complete set. That means, let us say x of t is a signal and there exists no x of t which is orthogonal to the elements of this set. So that type of set is called a complete set.